All right, let's get started. Hello, good morning, everybody. Welcome to those of you in Marcus and those of you joining the live stream. I hope you guys are all having an excellent week. Couple quick announcements. So as a reminder, we have our Chapter 2 quiz on Friday. Same structure as the Chapter 1 quiz, so it'll be 10 questions, multiple choice. And you'll need to find a 1-hour period to take that Chapter 2 quiz at some point on Friday. So it'll open at 12:01 a.m. And close at 11:59 p.m. So you can really take it anytime on Friday. So you can take it early in the morning before classes if you want. You can do it later that night, whatever works best for your schedule. As a reminder, there is a review session on Thursday. I sent an email, a class email about that with the Zoom link. And I will post that review on Thursday after it happens. So if you are not able to attend, you can watch that through the link on Moodle. Otherwise, today we're going to be finishing up Chapter 2, and then on Thursday we will start Chapter 3. So we're just kind of marching along, and we're on good pace. So I'm going to go ahead and switch over to the dot cam. Okay. And so today we're going to be covering two different things. We're going to be talking about the second derivative, which is an extension of the derivative function, which is the videos you watched last week on 2.2. And then we'll also talk about marginal analysis, which is an extension of the work that we were doing in 1.4. So when we talk about the second derivative, we sort of alluded to it a little bit last week on Thursday when we talked about acceleration. So there's a lot of instances where the second derivative might help us inform some situation about what's happening. And so the second derivative is going to tell us about the rate of change of the rate of change. So let's just consider an example. You can see here that I'll talk about just so we know why we might want the second derivative. So you may remember that BP had a pretty big oil spill. I don't even know how many years ago now, 12 years ago. And oil was leaking out of the boat, and environmentalists and scientists and people in all sorts of agencies were trying to figure out how long it would take for all of the oil to sort of leak out of the boat, because this was going to be a crisis situation for ocean life and things like that. So at first they were calculating the rate at which the oil was coming out of the hole from the hole that had come up in the boat. And that's represented by a first derivative. So how quickly is the oil coming out of the boat? But they quickly realized that what was happening is within the hole is getting bigger and bigger, which means the rate of change at which the oil was coming out of the boat was also growing. And so they had to quickly figure out how the rate of change was changing in order to determine how long they had until the entire vessel was emptied of all the oil, which we knew was pretty catastrophic. So, thinking about the rates of change can be really helpful in the moment to determine different things that are happening in real life. So the second derivative is something that's going to become important to us because the rate of change of a rate of change does have a lot of implications. Now, there are third derivatives, fourth derivatives, fifth derivatives, on and on and on. We are not going to consider those because they don't have as many practical applications. There are some in physics, but for the most part, the first and second derivative cover most of the things that you will need to learn and understand for your major. So let's start by talking about notation. So as you know, calculus was created in parallel by two different people. So just like the first derivative notation, we have two different sets of notation for the second derivative. So you will either see something that looks like this, which is Newtonian, and we say f double prime of x. So this is, the word prime. So f prime of x is the first derivative, f double prime is the second derivative. And then the other way you may see this, although this is less common, is with the Leibniz notation, and it looks like this. So either of these notations indicate that we are interested in finding a second derivative, okay? So before we actually get to the second derivative, we need to review what we know about the first derivative, because a lot of the work that we do and learned in 2.2 is going to help us understand how to get to the second derivative. So as a reminder, the key relationship that we were working on to think about the first derivative as a function was that if f of x is increasing on some interval, then the derivative is going to be positive on that interval. Because if you think about an increasing function and you plot some tangent lines, you can see that they are all positively sloped. If f of x is decreasing on an interval, then the derivative will be negative on that same interval where it's decreasing. And then finally, if f of x is constant on an interval, then the derivative will be 0 on that interval. So when we talk about constants, there's two places that that comes up. So a constant function could be a horizontal line, right? This is constant. But it could also be the point where we change from increasing to decreasing or decreasing to increasing. The point where we change what we're doing is also considered constant. Okay, so when we talk about being constant, those are sort of the situations we are considering. So the first example we're going to do, we are just going to work on practicing this first so that we can then extend it and build upon it. Okay, so our first example here, we're going to do two pieces to this. So consider the function f of x below. So this is some function f of x. We want to determine the intervals where the first derivative is positive, negative, and 0. Okay, so I want you to assume that this function goes on forever. So boop, boop, put those on there, right? So I want you to think about how we can use the original function f of x to determine where the derivative of prime of x is positive, negative, and 0. And that goes back to those three relationships that we just talked about. So that's the first part. That's example 1. Also, after you've done that, I want you to think about how we can take this information from example 1 and use that to help us graph the first derivative of the function. So we'll know the signs of the first derivative, and that will help us think about how to graph the first derivative of this same function. Notice that these are the same. So those are the two pieces, and you really want to do this piece first because that will help us think about this graph. And this is the same axes as the original function. So I'm going to give you about 3 minutes to really think about this. Again, we're trying to use the original to figure out the sign of the first derivative. And then once we have those, we're trying to graph the first derivative. So take 3 minutes, try that out, see what you can come up with, and then we'll go through it together. Okay, take about 30 more seconds. Okay. So what we're doing right now is we are analyzing an original function graph to get information about the first derivative. Okay, so this type of analysis is going to be really important. So we really need to think about the process and how we make these determinations, because this is going to help us build upon it for the second derivative later. So we're interested in three things, where the first derivative is positive, negative, and zero. You can do this in any order, but I find it helpful to start with the zeros because that helps me determine the intervals where I'm looking. So I'm going to do that first, but again, you don't have to. So I'm looking for places where I'm going to have a horizontal tangent line. So I'm going to have one here, and I'm also going to have one here. So it's not a coincidence that this is sort of at the top of a hill and the bottom of a cup, because these are the places where I'm changing from increasing to decreasing or decreasing to increasing. And so what does this tell me? So this tells me that the first derivative will be 0 at, and now I'm going to take the x values, so at x equals 0 and at x equals 4. Okay, we're always considering the x values where these things happen, because we could shift this graph up or down and this would stay the same because it's the shape of the graph. And we're asking where does it happen, which is the independent variable. So that takes care of where the first derivative has zeros. Okay, now we also want to know where the first derivative is positive and negative. So this is where we are looking at where our function is increasing and decreasing. So when your function is increasing, if f of x is increasing, then the first derivative is going to be positive. Okay, so looking at this picture, I'm thinking about when I go from left to right, where is it going up? So I see that that's happening in the first part of the graph. So I'm going to say that that's happening from negative infinity until 0. And I'm using open brackets because I know that at 0, I'm constant. But it's also happening over here. So notice that after 4, it's also going back up. So from 4 to positive infinity. And again, I'm using open brackets at 4 because at 4, I'm constant. But anything slightly after 4, I'm increasing. Okay, so that's what I'm looking for here. And then similarly, if my function is decreasing, that tells me where the derivative is going to be negative. So I look here and I notice that the piece that I have left, which is between 0 and 4, I'm going down from left to right. Okay. So from 0 to 4 is where my derivative is going to be negative. And I can confirm this because if I draw in a tangent line anywhere along here, I can see that it's going to have this negative slope. So now I know where my first derivative will be positive, negative, and 0. Okay, so I've analyzed the original function to get information about the derivative. So now I want to take that information and use it to construct a picture of what the first derivative is going to look like. And as a reminder, when I draw the first derivative, what I'm trying to do is figure out the slope of the tangent line at every single point, putting it together to make a function, right? So I'm going to start with the zeros because those are actual values, right? When x equals 0 or x equals 4, the derivative equals 0. So I have an actual value. So at 0, I'm at 0, and at 4, the value is 0. So I know my derivative has to go through those points. What else do I know? I know that from negative infinity to 0, so in this region here, so before 0, I should be positive. So that means I have to be above the x-axis somewhere. This is the positive quadrant. I also know that I have to be positive after 4. Okay, so over here, I also have to be positive, which is above the x-axis. Between 0 and 4, however, is where I'm negative. So I'm somewhere down here. So I have a function that starts up here, has to go through this 0, does some stuff here, has to go back through this 0 and end up here. And so from 2.2, we sort of learned some of the shapes that come up from derivative graphing. And so when I consider these tangent lines are getting less and less steep, that means I'm coming down towards this 0. And then in sort of the in-between phase, I know that my tangent lines are getting more and more negative, right, if I graph them, but then they start to go back towards 0. So more and more negative, back towards 0, and back up this way. So a rough sketch of what my first derivative looks like is this sort of U shape, where I'm positive over here and negative down here. Okay? So that's how we go about doing the work from 2.2, which was last week, thinking about an original function and then either knowing some properties of the first derivative or even drawing the first derivative. So now what we want to do is we want to take this derivative picture and think about how we can use this to then talk about the second derivative. And remember, the second derivative is the derivative of the first derivative, which means we can do the same type of work on this picture that we did on this picture to get to the next derivative. So what we're going to do is we're going to take this picture here, recreated, and we're going to do the same thing. So we have the first derivative here. Okay, and this is just a function, right? This is a function on its own, and we want to use this to determine the intervals where the derivative of this function is positive, negative, and 0. So we're going to do the same thing that we did over here, right? How did we figure out where we were positive, negative, and 0? We looked at increasing and decreasing. Same thing here. We're going to look at increasing and decreasing to figure out where the derivative of this function is positive, negative, and 0, because the derivative of this function is the second derivative. Okay, and just like before, once we figure out where the second derivative is positive, negative, and 0, we then want to try to graph it based on these properties. So I'm going to give you another 3 minutes. I want to do the same analysis on the first derivative graph to get information about the second derivative and see if you can graph that. Okay, so take 3 minutes and then we'll go through it together. Okay, take about 30 more seconds. Okay. So we have to be a little careful with the notation, but the process is going to be very similar to the last one we did, right? So I'm going to start by finding the zeros, but what I'm finding the zeros of are the second derivative because I'm going from the first to the second. So where are the zeros? So here I'm looking for a horizontal tangent line. And I see that that happens at x equals 2. Now, I want to figure out where my second derivative will be positive and negative. So here, if the first derivative is increasing, the second derivative is positive. So using the same process as before, if my function is increasing, then the derivative of that function must be positive. So here I see that I'm going to be increasing after 2 to the right of 2. So from 2 to infinity, my second derivative will be positive. Similarly, dropping my pens here. If the derivative is decreasing, the second derivative will be negative. So I look at my function, I see that before the 2, my function is going down from left to right. So I'm decreasing over here. So negative infinity to 2 is where I'm decreasing, which tells me that that is where the second derivative is negative. So now that I have these intervals, I want to think about how that impacts my picture. So again, I'm going to plot my 0. So the second derivative will equal 0 when x equals 2. So I come over here to x equals 2, and I know that the y value will be 0 from this statement. Okay, so here's 1, 2, 3, 4. So from my work, I know that from 2 to infinity, so after 2, my function should be positive. Somewhere up here. And that from negative infinity until 2, my function has to be negative. So I have to start down here. I have to go through this 0, and I have to end up here. So we know from our work in 2.2 that if I started with a U-shaped function like this, that when I draw the derivative, it's usually linear. It's roughly linear. So here, I'm going to have a function that starts down here, goes through 2, and ends up here. So when I have this picture, the derivative of this looks like this. So that means I now have 2 sets of statements to work from, okay? And what I'm doing is I'm bringing the relationship that I had before and applying it to the first derivative. So if the first derivative is increasing on an interval, the second derivative is positive on that interval. If the first derivative is decreasing on an interval, then the second derivative is negative on that interval. And if the first derivative is constant on an interval, the second derivative is 0 on that interval. So this is the same statements we had before, but instead of going from f of x to f prime of x, we are now going from f prime of x to f double prime of x. So we now have relationships between the original and the first derivative, and the first derivative and the second derivative, right? That's what we were doing here. What we don't have yet, however, is what the relationship between the original function and the second derivative is going to look like. So, as a reminder of what our picture looks like here, our original function looked like this, and our second derivative looks like this. So what we need to do is we need to think about if there's a relationship between some property of the original function and the second derivative. That's sort of our mathematician goal here, right here. So what I'd like you to do is just take a minute and really think about how we might be able to relate these two things. And I want to remind you of the three ways that we describe graphs. We have positive, negative is one category, increasing, decreasing is another category, and concave up, concave down is a third category. So we want to think about if there's a relationship of one set of properties for one of these graphs to another set of properties on the other graph. So take a minute just to look at it, see if you can think about what may work, and then we'll go through it. Okay, take another 30 seconds to see if you can figure it out. Okay, so if you look at the concavity of the original function, so this is concave down, and this is concave up. Okay. That directly maps. So notice that we are concave down from negative infinity until 2 to where the second derivative is negative, and then we're concave up from 2 on, which is where the second derivative is positive. And then the second derivative is 0 right at 2. And so at 2 is where we have what's called an inflection point. And an inflection point is the point where we change concavity. Okay, so it turns out that there's a relationship between the concavity of the original function and the sign of the second derivative. Okay, so all of our relationships are based upon things like increasing, decreasing, positive, negative, concave up, concave down. And what our job is going to be is to try to keep straight which relationships tell us which things, which is sort of the tricky part. So here are the three sets of relationships, okay? So we have f of x is increasing, the first derivative is positive. So this is giving us a relationship between the original function and the first derivative, and those are the ones we started with. Our second set of relationships is between the first derivative and the second derivative. So when the first derivative is increasing, decreasing, or constant, it tells us the sign of the second derivative. And then our third set of relationships are the concavity of the original function and the sign of the second derivative. Now, what's tricky is you never really know which relationships you're going to need to use until you really understand what you're trying to find. So you may be given information about the second derivative and asked questions about the original function. So then you're going to want to think about the relationships we know about the second derivative and the original function. But I could also give you information about the first derivative and ask you about the original function. So that's where these come in, first derivative, original function. So whenever you're doing a problem now and you're analyzing these types of relationships, the question is, what information do we have? So do we have a table, a graph, a word problem about the original, the first derivative, or the second derivative? So what do we have? And what do we want? Do we want information about the original, first derivative, second derivative? Because once we can identify what we have and what we want, we can pick the correct set of relationships to use. Okay, so we need to be really careful as we're doing problems to make sure we understand what we're given, what we want, and then we can pick accordingly. These relationships are going to be really important. And so this is one time that I'm going to recommend that if you don't have the guided notes printed out, that you write these up and you keep these on a piece of paper, easily accessible, maybe at the front of your notebook, because these are going to come up time and time again. And so to have them as like a handy reference on its own sheet will be helpful for you as you move through different things. Okay, so let's do some practice problems using these relationships. So we're going to start with this problem here. So we have this function, and this function is an original function. Okay, so this is f of x. We want to use this function to figure out whether the following things are positive, negative, or 0. So what we're doing is we're evaluating what's happening at -2, at 0, and at 2.5 for the original function, the derivative of the function, and the second derivative of the function. So I'm going to mark each of these. Okay, so -2 is right here. 0 is right here. And 2.5 is going to be right here. It doesn't quite look like 2.5, but that's because I traced it weird. Okay, so for each point, you're going to determine, is the functional value positive, negative, or 0? Is the derivative at that point positive, negative, or 0? And is the second derivative at that point positive, negative, or 0? So the second derivative is what we added today. And so we're looking at concavity at these points for the second derivative piece. All right, so I'm going to give you 2 minutes. Think it through, look at what we know, think about what you remember, see what you can figure out. And for each one, you're going to put either a plus, a minus, or a 0. And then in 2 minutes, we'll go through it together. Okay, take about 30 more seconds. All right, so let's start by looking at what's happening at -2. So that's the point we're going to evaluate first. The functional value, f of -2, is asking, is the y value at that point positive, negative, or 0? Since this is below the x-axis, that means f of -2 is negative. Okay. The derivative at -2 is asking whether the function is increasing, decreasing, or constant at that point, because that will tell us if the slope of the tangent line is positive, negative, or 0. we can see that at this point we are decreasing. And if we were to actually sketch in a tangent line, we would see that it's also negatively sloped. So the derivative at -2 is negative. And then finally, for the second derivative, we have to consider the concavity. And so this is a little tricky. So we really want to think about where it changes concavity, which is here and here, because this whole piece right here is concave up, which includes what's happening at -2. So -2 is still in the part that's concave up. If the second derivative is concave up, then we have a positive second derivative. Okay, so now let's look at what's happening at 0. So again, we start with f of 0, and we're asking, is the y value positive, negative, or 0? Well, this is above the x-axis, so that will be positive. When we consider the slope of the tangent line, we are constant here. We have a horizontal tangent line, so the derivative will be 0. And then we see that on this interval, this is all concave down right here. So that means the second derivative is going to be negative. Finally, we go over to 2.5, right? And again, we start with the functional value. We see that that's right on the x-axis. So the functional value will be 0. For the derivative, we see that we are increasing through 2.5. We're going upwards. If we're increasing, the derivative is positive. And then for the second derivative, we can see that to the right, we're concave down, but to the left, we're concave up. So this looks like exactly the point where we're changing from concave up to concave down, which means that the second derivative is 0. So one of the main points I really want to emphasize here is that just because one of these things is positive, negative, or 0 doesn't tell you anything about the other ones. Like just because the functional value is negative doesn't tell you whether the derivative or second derivative will be positive, negative, or 0, because we're evaluating different things. The original, we're looking at positive, negative. First derivative, increasing, decreasing. Second derivative, concavity. So really the only way to determine these signs is to understand what you're looking at that point on the graph to make that determination. And that takes a little bit of practice, and that's why having those sort of rules is really helpful. Okay, so let's look at another example and see how we can apply what we've learned to some tables. So we have two tables below. I want you to notice that the first table, you have some x values and some f of x values. The second table, you have x values and f prime of x values. So these are derivative values. These are two different unrelated tables. We're just thinking about the difference in how we would solve these. So given these tables below, we want to figure out where the original function is most likely to be concave up and concave down. Okay, so thinking about our rules, I'm just going to point out a couple things here. I'm going to bring these rules back for a second. We want to know about concavity. Where does concavity show up? Here. In order to determine concavity, we need to know the sign of the second derivative. Okay. Need the sign of second derivative. Neither of those tables had the second derivative. Okay. One of them had the first derivative and one of them had original functions. What can we do to get the sign of the second derivative? Well, this is the sign of the second derivative. So we can use the first derivative to get the sign of the second derivative, and then use the sign of the second derivative to get the concavity. So for both tables, we're going to need to think about how we can use the first derivative to get the sign of the second derivative. We have the first derivative here. We don't have it here. So we know how to sketch out a first derivative now on a table. We've done that a few times. First with the average rate of change, then we made it better with the instantaneous rate of change. So I want you to try to figure out what you can on these two tables. I'm going to give you 3 minutes, see how much you can figure out, and then we'll go through it together. Okay, take about 30 more seconds. Okay. So we know from looking at the rules that we need to have information about the first derivative to talk about the second derivative. The second table gives us the first derivative, so that's good, but the first table doesn't. So we're able to come up with an approximation of the first derivative, again, by doing the change in y over change in x. So for any of the middle points on the table, you would use the 2 points around it, and for the end points, you do change in y over change in x with a point right next to it. So we get a sketch of the first derivative that looks like this. So now both tables have first derivative information. So what do we want to do with that? So I want to remind you from our statements, if the first derivative is increasing, the second derivative is positive. So I want to think about where we are increasing and decreasing. So here, 2, 2.5, 3.5. Those are all increasing values. And that tells me that in that interval, the second derivative is going to be positive. And then I want to consider where I'm decreasing. So 3.5 to 3.5, that's constant. But 3.5, 2.5, 1.5, 1, those values are going downwards. Those are decreasing. So the second derivative is going to be negative on that interval. And what about this 3.5, 3.5, right? So that's the same. So that's going to be constant. I'm going to put CON. And we said that the second derivative will equal 0 if the first derivative is constant. So the reason I wanted to get the first derivative is to figure out where it's increasing and decreasing, which is going to tell me where the second derivative is positive and negative. The reason why I want that is because when the second derivative is positive, the original function is going to be concave up. Okay. And when the second derivative is negative, the original function will be concave down. And when the second derivative is constant, is where the original function is most likely to have an inflection point. Okay, so how do we finally answer this question? It's most likely to be concave up from x equals 1 to x equals 3. We're using the independent values to talk about where things are happening. So we're going to be concave up between 1 and 3. And we're going to be concave down from 4 to 7. Okay, so that answers the question, where is it most likely to be concave up and concave down? Now we're going to do the same type of analysis on the second table, okay? But again, we were given the derivative value, so we can jump right to the point where we're seeing where we're increasing and decreasing. So here I have 2, 5, 6, 12, 17. Those values are all increasing. If we are increasing, that tells me my second derivative is positive. If my second derivative is positive, that tells me that the original function is going to be concave up for those x values, which is 1 to 5. Okay. Similarly, I now look at where I'm decreasing. So 17, 14, 11, those values are decreasing. When the first derivative is decreasing, that tells you that the second derivative is negative. If the second derivative is negative, that tells you the original function is concave down. And that's going to happen for x between 5 and 7, that interval. Okay, so this is really meaty analysis, right? This is where the critical thinking comes in. This is not something you can just plug into a formula. You really have to understand these relationships and what sorts of information they tell you. So this can be tricky for some people. If most of your mathematics has been mostly formulas, then doing this type of work can be really complicated at first. The more you work within these relationships and think about what they're telling you, the more you understand the underlying properties of the analysis, right? So this is analysis and critical thinking. This is not algebra and formulas, right? So we need to practice with these statements, and they come up a lot of ways throughout the course. So really, the more you can practice these early on and really start to work out how these all interact with each other, you know, the better overall it'll be when you have to use them in sort of other types of contexts. So one thing I will recommend, which I think is really helpful if you're struggling finding like these relationships, is to create like a chart. And I'm going to show you an example of the chart that I usually have students do when they have trouble remembering this type of stuff. So creating a chart that kind of looks like this, where you have f of x, f prime of x, and f double prime of x, same thing across the top. And we write the statement, if we have this, so if we know something about f of x, then we know this. So what does f of x tell us about the first derivative? Well, if we know that f of x is increasing, then we know the derivative is positive, right? In this box, we'd have something like, if f of x is concave up, then the second derivative, you know, is positive, right? Things like that. So filling out this chart will help you sort of understand this relationship. And then later on, if you're looking at a graph and it's a graph of the second derivative, then you would go here, we have this. And now you can answer questions about the original or the first derivative based on that, right? You can obviously answer questions about itself from before calculus, but I find generating this chart to think about it helps make those connections, okay? So that's the second derivative. As I mentioned, we're also going to be talking about marginal analysis. So we're going to shift gears, and marginal analysis is something that we started in 1.4. We started it a little bit early, and we talked about what that looked like for linear functions, right? We said, okay, we're just going to assume in 1.4 that everything is linear, right? And we said that marginal revenue, marginal cost, marginal profit, that is represented by the slope of the linear function, right? That was the rate of change that we knew at that point. However, we've now done some work and we know more about other types of functions that are not linear. So we're going to talk about what marginal analysis looks like if you have something that maybe isn't linear. So again, we're going to sort of broaden our definitions here. So marginal cost, which we're going to notate as C prime of Q, so the derivative of cost, is the additional cost to make one more item. So as a reminder, when we talk about cost, you're thinking about it from a manufacturer standpoint. So you are the one making the items that you're going to be selling. And so how much more does it cost you to make one more? That's marginal cost, okay? And so with marginal cost, we said if the cost is linear, right, which is the premise we were working on before, then the marginal cost was the slope of the line. So whatever the slope of this line was the marginal cost. But if the cost is not linear, right, so now if we're considering something that is no longer a line, then the marginal cost is the slope of the tangent line at Q star. And so Q star is just whatever quantity you're considering. So we know now that the slope of the tangent line will tell us the rate of change at any point. So if it's not linear, right, then we have to draw on this tangent line and approximate it. Okay, and that's what we've been doing with other functions that are not cost, right? So now let's talk about marginal revenue. So marginal revenue is going to be R prime of Q, the derivative of revenue is the additional revenue from selling one more item. Okay, so again, we're making something and we're selling it. So when we sell it, right, we were talking about price times quantity in a linear scenario. And so if we sold one more and we were charging $10, we get another 10 bucks, right? So if revenue is linear, then the marginal revenue, again, was just the slope of the line. Right? However, if revenue is not linear, then the marginal revenue is the slope of the tangent line at the point that we're considering. We're just going to call that Q star. Q star is just wherever we're trying to evaluate it, right? We need to approximate the slope of the tangent line. And so marginal revenue is the pi prime of Q is how we notate it, is the additional profit from making and selling one more item. Okay, and we can calculate that by doing marginal revenue minus marginal cost. So if we know the additional revenue we take in from selling one more item and the additional cost from making that item, then the marginal profit is the difference between those two. So one thing that becomes really important in marginal analysis for cost, revenue, and profit that is different from general derivative calculations is that in our definitions here, it's always talking about what happens when you make or sell one more, which means that when we do our approximations, we are always looking at what happens if we add one, which is a right-hand approximation. Because in business, right, we already know how many we've sold up into a point. So the question is always, what happens if I do one more, right? We don't predict backwards in business because we already have that data. So we're always going to be doing a right-hand approximation when we have to approximate the derivative, which is different than a generic function where we would do a left and a right and average them together. Okay, so that's a little bit different and a little bit tricky. So let's keep that in mind as we try some practice problems. Okay, so the first two problems that we're going to try, example 1 says, suppose that the revenue for a certain item is given in the table below. Determine the marginal revenue at Q equals 15. So we're approximating the derivative on a table, right? So we're looking for R prime of 15 based on the table. And then for the second example, suppose cost is given in the graph below. So we have a linear cost. We are trying to figure out the marginal cost at 10 units. So we're trying to approximate C prime of 10. And then the second example has a part B. So after you've computed C prime of 10, the question is, if R prime of 10 is 15, so we also are given a marginal revenue, then what is the marginal profit for this item at this level? Okay, so I want you to take 3 minutes, see if you can try out these two problems by applying what we know about approximating derivatives on a table and on a graph, and remembering that we have to always use a right-hand approximation in business. See what you can figure out, and then we'll go through it together. Okay, take about 30 more seconds. Okay. So for example 1, we have this table and we want to approximate the marginal revenue at 15, which is here on the table. And since we are talking about a business application, we are going to use the information to the right, okay, right-hand approximation. So to approximate the derivative, we'll do the change in y over change in x. So 180 minus 160 divided by 20 minus 15. That's going to give us 20 over 5, which is 4. So the marginal revenue is $4 per item. And so what does that mean? That means if we were to sell one additional item, so we were selling 15, if we now sell 16, we take in an additional $4 in revenue for every additional item that we sell at this level, okay? Now, for the next one, we're looking for marginal cost. And so what I want you to notice here is that the cost function is linear, okay? And so if your cost function is linear, we said that the marginal cost is just the slope of the line. So we want to figure out the slope of this line. And so what I'm going to do is I'm just going to pick 2 points on this line to figure out the slope. So you can pick any 2 points on this line. You may not have picked the same points that I picked. That's totally fine. You should get the same approximate answer. But we just need to find the slope of the line because this is linear. So I picked the points 10, 150. So 10, and then it looked like it was about halfway between 1 and 200. And then over here, I picked the point 30, 300. So now to get the slope of the line, I'm going to do change in y over change in x. So 300 minus 150 over 30 minus 10. And that's going to give me 7.5. But since we're talking about money, we want 2 decimal places. So it's going to be $7.50 per item. So what does that mean in practical terms? So if I am producing 10 items, it will cost me an additional $7.50 to make one more item. So to go to 11 items, it's going to cost me $7.50. Okay. Now for part B, we're told that the marginal revenue at 10 items is $15. So that means that if I were to sell one additional item of whatever it is I'm making here, the revenue I would take in would be $15. So to go from 10 items to 11 items, I would take in an additional $15. So if I want to talk about the marginal profit for this item, the marginal profit is going to be the marginal revenue minus the marginal cost at the same level, right? So the amount of extra money I bring in, which was the $15 per item, minus the additional cost, which I found in part A, was $7.50, which means the marginal profit at that level is $7.50. Oops, marginal profit. Okay, so marginal profit is the additional profit I get from making and selling one more item, right? So if I were to make and sell an 11th item, so going from 10 to 11, I would expect an additional $7.50 in profit, because that's the difference between the additional money I take in plus the additional money I spent. Okay, so the next example, the actual question itself is not terrible, but there's a lot of analysis that's going to happen behind the scenes of this graph that we're going to need to talk about. So I want to talk it through, and then I'll have you try the other example after, but there's a lot of information I want to give you that's not asked in this question, but is relevant to this type of picture. So example 3 says, consider the graph below and determine when this product is making a profit. Okay, so what are we looking at here? So we have a cost function in blue that is not linear. And then we have a revenue function in red that is linear. And the question itself is, when are we making a profit? Okay, so think about profit. Profit is revenue minus cost. So when we say making a profit, what we really mean is, when is the profit positive, right? So when are we actually making money? And so in order to be making a profit, we would need our revenue to be more than our cost, right? We need more money coming in than we're putting out. So what we can do is just kind of think about where these intersect, right? And we can see that in this little area here is where revenue is greater than cost, right? So this is going to happen, right, for quantities between 130 and 215 approximately, right? So this is like our little profit. I was going to call it a bubble, our little profit interval, okay? And that answers the questions. When are we making a profit between 130 and 215 units? But, and this is a really big important asterisk here, not all profit is created equally, okay? So one question that we talk a lot about in economics and business is, should we make more, right? Does it make sense for our business to make more? And you may think that as long as you're making a profit, you should make more. And that's a completely normal thing to think. However, I want you to think about this idea of profit as revenue minus cost, okay? And when you think about being in a business, I want you to consider that you are a greedy business person, that you want to make as much money as possible, right? It's sort of like capitalism, right? So that means that we want to find the place where the revenue and cost are the furthest apart, right? That's going to be our maximum profit, is where the difference between revenue and cost is the greatest. So if the difference here is like $100 profit, then the difference over here might only be $30 profit. That's not as good, right? So within making a profit, there are better places to be than others, okay? Now, that being said, one of the things that's going to come up for us throughout the course is, how do we decide if we should make and sell more of an item, okay? And this has to do with comparing the marginal analysis of cost and revenue. So over here, before we're at the max profit, okay, the marginal revenue and the marginal cost are going to look like this. So marginal revenue, marginal cost. So in this area here, what I want you to notice is that marginal revenue is greater than marginal cost. What do I mean by greater? The slope of this line is steeper than the slope of this line. So what does that mean? That means that if we make one more, the profit is going up, right? Because remember, marginal profit is marginal revenue minus marginal cost. So if this is bigger, then marginal profit is positive. So if marginal revenue is greater than marginal cost, we want to make more of whatever it is that we're looking at, right? Because we are trying to get to this point right here, the max profit. When you are over past the max profit and you think about marginal revenue and marginal cost, what you will notice is that over here, marginal cost is greater than marginal revenue. So the slope of the marginal cost line is steeper than the slope of the marginal revenue line. That means that marginal profit is going to be negative, that you are not making additional profit being over here. So we do not want to make more. when marginal cost is greater than marginal revenue, because that means we're moving away from the max profit, and we always want to move towards it with business decisions. So that is a question that's going to come up throughout the course. Should we make another one given this picture or given this information? And so these two sort of statements are things that help us understand that decision. So if you have information about the marginal revenue and the marginal cost, and the question is, should we produce more of this item? We need to determine which one is bigger. If marginal revenue is bigger than marginal cost, yes, make more. But if marginal cost is greater than marginal revenue, do not make any more, because that means you're moving away from the profit. So in summary, profit is good, but there are within profit better places to be, right? So just because you're making a profit doesn't mean you should make more of the item, because you want to maximize your profit. Okay. Okay, so finally, example 4, we have a cost function, and we're told that to produce 15 items will be $2,600, and that marginal cost to produce 15 items is $109. Okay, so we want to try to use that to approximate the cost of producing 20 items and of producing 10 items. So if you have information about a function and the derivative, and you want to use that to approximate the cost at another point, this is local linearity. So this is what we were doing at the end of the last class, okay, by approximating using the tangent line approximation. So we're going to try to do this here. I'm going to give you 2 minutes, see if you can work out A or B. You probably won't have time to do both. But see if you can remember how we used the tangent line approximation, also known as local linearity, to approximate a different point on our function. Okay, so take 2 minutes, and then we'll go through it together. Okay, take about 30 more seconds. I want to make sure we have enough time to go through at least one of these so that you know how they're done. Okay, so remember, with local linearity, we are trying to approximate something we don't know, which is C of 20 and C of 10, by using information at a point and the derivative at that point, right? So to approximate this, we're going to take what we know about the cost to produce 15 and the rate at which we are changing the marginal cost for both of these. That's the information we have. But then we have to multiply the derivative by how far away we're looking. And we said order is important. So here we want to know what's happening at 20, but we're using 15. Here we want to know what's happening at 10, but the information we have is about what's happening at 15. So we fill in the values that we know. 2,600 plus 109 times 5, 20 minus 15, And then here we have 2,600 plus 109 times -5. Now this one's a little goofy because we talked about how in business, we always like to figure out what's happening going ahead. The one caveat to that is if you are trying to understand a competitor's business model and you have some select data, sometimes you use it to look back, but this is one of the only instances you would do this. So I just want to remind you that you're going to do the multiplication first and then add it to the 2,600. So in the first case, we get $3,145 as our approximated cost to produce 20 items. And then here, because this is negative, we add a negative number to 2,600 and we get $2,055 as our approximated cost to produce 10 of these items. And that should make sense because the cost to produce 10 items should be less than the cost to produce 15 items, 2,600, which should be, even less than the cost to produce 20 items. So they should go in order because we know cost is an increasing function. Okay, so try out, the homework and the mini quiz. And just as sort of a suggestion, if there's outstanding mini quiz questions you didn't understand, make sure you go to drop-in help before the quiz on Friday to go through them so you understand why you got them wrong. Okay, have a great day and I will see you guys on Thursday.